Should we download the new release from MATLAB? Okay, you can all sing it. You can download it.
So, you know, I feel like the new releases are like the stuff that's new. You're not gonna use it. I mean, so you can do it. I don't think you'll ever. There may be a look and feel change. I don't know if there is one this time around. It's just what? Well, yeah, it's true. There are the licensing is sometimes annual, depending on your license. Yeah, that might be what it is. We're on. We're on. Okay, I just want to talk a little bit about the errors, pitfalls thing. I want to talk about two distinctly different types of errors. One that you're very familiar with, and the second one that I think we're going to start experiencing a little bit more, and that we're not as familiar with. The first is the syntax error. This is the one that MATLAB actually tells you about. It's probably the most common type. And it's typically a result of using the wrong command or a typing error or the wrong format, right? Result of typo, wrong command. Sometimes it's the wrong symbol, right? You were supposed to use square brackets, we use circle brackets instead. And these are typically fatal. And fatal just means the program execution stops, it halts. MATLAB typically gives you a cryptic error message. But perhaps they're starting to feel a little less cryptic than they were at the beginning of the semester. I hope most of you are starting to feel like, I think I can understand what MATLAB is trying to tell me on this. Maybe it's not full clarity, but at least you're starting to get into the habit of kind of interpreting. These we've seen already, yeah? A lot of them. The next one is actually way more important. And these are called logic errors. These are effectively errors in your algorithm. And the reason these are a challenge to find or determine is that the program runs. MATLAB runs to completion. No MATLAB complaint. So what's wrong? The result, the answer that you got is incorrect. Yeah? And the worst part about it is you might not know. It may not be completely obvious, right? You did the myfact n factorial. There was no MATLAB errors. We did n factorial of 4, and you got 200. That's an example of logic error. Right? Something's wrong in your algorithm. So, how do we check this? These are habits you should get into if you're going to start writing programs, scripts, functions for any sort of work application or any of your other classes. You cannot trust that your algorithm is perfect without doing some validation and testing it. Run the program for special cases for which you know the answer. You can run the program for corner cases, extreme values. Choose really small, really big ones. People call these corner cases. You think of all of the cases you could run as being a field of cases. Pick the ones that are way in these corners, in the niches of your sort of value frame. system of values. If you don't have precise answers, you check the order of the magnitude, the ballpark. Is the order of magnitude of the result? Does it make sense for the problem I'm trying to solve? Is everyone familiar with this order of magnitude term? Order of magnitude is like 10, 100, 1,000, right? If you're doing some analysis for something, let's say you're doing a stock and flow script for some chemical engineering process, and you know you started with 5 gallons of input material, the order of magnitude of your end result should be in the 0 to 10. First order of magnitude. If the result ends up being 12,000, that's 3 orders of magnitude off. And that's your hint that you're not in the right order of magnitude. Another way to think about it is the ballpark. Are you in the right range of correct values? And also try to work through the problem by hand, like step through the MATLAB code, just like we did in our factorial exam. Okay with that? Any questions on sort of this approach? This approach to debugging to make sure your logic, your algorithm is correct. I raise this slide. You might need this. You might need this. Speak now. Speak now. So connected with this is this concept of exceptions. Exception exception refers to an error that occurs during the program running that is neither syntax nor logic. It's that you got into a situation you did not expect. Yeah? So this is not syntax, because syntax MATLAB is going to tell you right off the bat. And it's not a logic error, because logic errors are never going to cause the termination of your execution. And we don't really worry about it. We're not going to worry about it in this class, but I want you to sort of know this concept. When you start getting into more, like you start building code that maybe you'll share with your colleagues or whatever, you might want to start handling exceptions, right? So there's this concept of exception handling. Which effectively just refers to gracefully handling this error. Most programming frameworks, including MATLAB, have built-in functions, etc., to help allow you to handle exceptions. Right? And what you can do in exception handling is an error, MATLAB's about to throw an error, it's going to halt execution, and instead, it'll start a special function that you built, which is your exception handling function. In that function, you get a chance to sort of check some variables, see if things were out of parameter, out of bounds. Maybe you're trying to do a divide by zero. Divide by zero, where your zero is a variable, is a classic exception, right? So if your code has any divide by x, you've got y equals blah, blah, divide by x. That's not a syntax error. It may not even be a logic error, but given certain input parameters, x is 0, you've got divide by 0, you can get an error, right? And so how do you have MATLAB handle this? Is exception handling, or any program. And you could do some checks, some checks for values, some checks for parameters, checks for scale. Then you could print out some messages to the console and let the user know, hey, MATLAB is halting. Check this value, okay, check this value, okay, check these values, not okay. And that gives the user a sense of like, okay, maybe these are input parameters that weren't right. That's exception. Slightly more advanced, but you might start thinking about doing that, especially if you start using some of this MATLAB stuff in the other classes. Which is a good segue into the next topic, which is looking at dynamical systems. This is chapter 12 of Han. Han has many examples in this section, and there's more than I have time to talk about here. I picked out 2 that I thought were fun and interesting. One is kind of a mechanics problem, statics problem, if you will. And the other is a physics problem, basic physics problem. Similar to ones we've seen already. So let's do the dynamical system of the cantilevered beam first. Has anyone read this part of it? No, it's so sad. It's okay. So imagine you're building a building. Anybody use like XKCD? My drawings of humans are pretty much XKCD. And you want to build a patio that extends out a really long way. You're going to use one beam for it. That's a cantilever beam. And what you want to be able to do as a structural or mechanical engineer here is be able to say, okay, I'm going to have all these forces on here. And what I want to know is basically how much this beam is going to deflect. Okay? And there's actually a great reference in Han to this classic book that I completely forgot about. It's called Formulas for Stress and Strain by Rourke. And if you go look on it online, it's great. It's got like every equation for every scenario you'd ever imagine for these types of things and other structures. So if you're interested in mechanical stuff, go look it up. It's really cool. If you look carefully, you might be able to find a PDF. It's not that hard. So from that book, Han tells us that there's a fairly complicated equation that he then converts to a simpler equation which we can model easier now. But the equation looks something like this. The deflection of this beam. So what we're going to do now is convert this into a mathematical problem where we say this is our x-axis and this is our y-axis. Okay? And we are going to give values for y, which are along the x. So given a certain x, what is the deflection? Y is our deflection value. Does that make sense? Yeah, y is the deflection value. Okay. So we get this equation, which is, I actually think for me, there's something wrong in this equation, and I was not able to get to the bottom of it, but we don't use that equation, so I'm fine. I actually think there's something wrong. And I checked both 2 editions of Han. I still think there's something wrong. Okay, and so what he's saying here is this deflection is dependent on a bunch of factors here. E is this thing called the modulus elasticity. It basically is a characteristic of the material that this beam is constructed out of. How elastic is this beam? So you can imagine if it's like gummy bear, it's very elastic. And if it's steel, it's some elastic. And if it's concrete, it's far less, right? Then we have I, which is a bit of the profile of the beam itself. It's the moment of inertia. And then the omega is the load per unit width of the beam. Load per unit. So Han starts with this, and he's like, okay, this is too complicated. Let's provide a dimensionless equation for this thing. I don't know I do not know how he drives the dimensionless equation. But for the point of like, this is not a class in mechanical stress, but a class more in modeling. He simplifies this model with given these inputs. He simplifies it to this. And again, I'm not exactly sure how he got here. removing all dimensions. And what I mean by that is, notice these are capital Y's and capital X's. That capital X, I know, that capital X is lowercase x over L, okay? And L refers to this endpoint. And X is your point across here. So what he's effectively said is we're taking dimensions out of this. This is the whole, and everywhere along here is a fraction up to the whole. So it becomes independent of the length of this thing, really. I don't like it, but whatever. It's just to show the example that we can do. That also means the amount of deflection here has no meaningful dimension, right? We're just going to see the shape, but we're not going to see dimension. Is everyone okay with that?
You mean like no length? No.
Right. It's effectively just ratios. There's no inch or minute, meter, etc. Okay, so this is the equation we're going to use. It gives you the y values for your x values. Are you okay with that?
And the X is up or out through down.
Yeah. But we're doing it as a fraction of 1.
Yeah.
Right? Because it was defined as this, where L is the length of the beam. So it's a fraction of 1. Yeah. All right, good. Zoom out. I could be completely wrong about that equation being wrong, and that it's probably right, considering that it's been a very long time since I've done any statics or stress testing. Why? Sure. All right, so I'm going to make me a little script, and you guys probably need this on, right? You guys don't yell at me when I'm supposed to. Dude, teach, yo, teach. All right. So we are going to model a vector of x values. Now, those x values are going to represent this beam from the left, from my XKCD guy, all the way to the end. But it's all as a fraction of 1, right? So what do you guys suggest I should use for my x vector? So 0, I want to go 0 to 1, right? And what increment? 0.001 sounds great. So what's my syntax to do that? 0 colon 0.001 to 1. Perfect. Okay, great. So now I have a vector of x values. That represents all the values that I'm going to model across here, right? So how do I then compute these deflection values? Do I have to do it 1 by 1? I can do vector math, right? Totally vectorized here. Super easy in MATLAB, right? No loops required. How do you like that? Okay, so what is that equation going to look like? Y equals?
I don't know where you put the you do any X code? What's that last one? The GX squared?
Sorry, that's a 6.
You can start with the negative.
Got a negative, okay.
Hey,
Negative.
Now we're on a roll. Parentheses. And then we can do x dot carry forward.
Do I need the dot? What do you guys think?
I think so.
It's a vector, right?
Yeah.
Can I square vectors?
You do the dot if you want to do it individually for each statement in the vector, right?
Whoops. The second one. Ignore the first one. I had lowercase x. Yeah, so if I do square, it's like x times x, right? It's going to get me into matrix math. It's going to check the dimensions conforming, and the dimensions aren't conforming here, right? In fact, if you recall, what are the only types of, what is the dimension requirement for a matrix to square it?
N by N.
It has to be a square.
Yeah.
It has to be squared.
Yeah.
All right, cool. All right, so that's not going to work, huh? So we need the dot. Need the dot. Okay?
Minus. Dot minus?
Do we need the minus dot?
No, I'm messing around.
Wait, that's a thing?
No, it's not. I mean, MATLAB may let you do it, but there's no need for a dot in minus and plus. Matrix addition and subtraction is no different. It's element by element. Cool. Minus.
Dot here.
Hey, how come I don't need a dot here?
Or does? No, I can do that.
4 is a scalar.
4 is scalar, right? So since 4 is scalar, there's no confusion here about matrix math. Simple. Okay? Times what?
X dot.
Dot caret 3.
Plus 6.
Okay?
What are you doing?
Plus 6.
Carrot? Plus carrot?
Oops. Thanks. 6 and caret are happen to be on the same key.
Dot caret.
Okay, perfect. Yeah?
That might be one.
All right, great. And then I'm going to make a placeholder here called YE equals 0. That is, yeah, I don't need that. Yeah, I don't need that. Skip that. Okay. So I have my values. What do you think I should do with my values? Visualize it, right? Yeah, exactly. Okay, good. So let's do that. I want to plot x and y. How would I do that? Plot
X.
easy, right? X comma y. MATLAB makes this so easy. I'm going to do some. Just make it look a little nice. We'll do that, and we'll run it. Woohoo! Look at that.
Yeah.
Now that's some serious deflection.
You can scale it, right?
Yeah. So let's do it. What I want to do now is put in a solid line for the not deflected beam, so we have something to look at against it. So I could do this by adding an additional plot on this line, right?
So like X equals 1 or Y equals 1.
So we'll just do it super easy, like so. Yeah, 0, 1. Lowest appears.
Well, wouldn't you go like 0:1?
I was just gonna do 2 points.
Oh,
0, comma
check
0 to 1, comma 0.
Oh, because
Yeah. Huh. It doesn't like it that way because why not? Why not?
like saying the 2 is the X for some reason. Instead, the Y goes to pair.
There. Okay, getting closer. How do I adjust the axes? You guys know how to do that?
Axes.
Yeah?
Yeah, exactly that.
What do I get it? What do I get it? you want it to be, you want the y-axis to go above. You give it x initial, x final, so 0, 1, and then you give it. Oh, there you go. Then you give it y initial, y final. I think the y was going down to -3. Yeah, there you go. Let's do that. Cool. There we go. Okay, and then you guys seen Legend? You guys have seen Legend, right? Okay. How does Legend work? Do you guys remember?
It's gonna, whatever name you give, it's gonna name that sequentially to whatever you plot.
Exactly. That's the key, is the sequential business, right? Cool. All right. Super small up here in the corner. You see it? Is that better? This is probably the simplest example in chapter 12, but you see that you can start modeling physical systems. Right? And I have started thinking a little bit about the projects for the last part of the semester, and I think one of them I'm going to definitely make some sort of stress analysis. But I have to figure out how to make it so it's manageable for all of you. I haven't figured that out. I have a bunch of ideas in my head for the projects. Maybe my sneak peeks right now. So one of them is some sort of structure, like maybe a bridge, and sort of figuring out the forces on the bridge. Another one is doing some image analysis. This is a project that I gave many years ago that caused a lot of heartache, but some people really liked it. And that was to take a black and white image of nuts and bolts and count how many nuts and bolts there were. And then the third is I wanted to throw out a project to do sound file compression. So those are the three I have in my head so far. And they may seem daunting, and so I have to figure out how to make them so they're not daunting, but challenging. Challenging, but not daunting. Remember, that was going to be the one where you pick, right? You pick from the list. I think everyone thought that would be a good idea. So, yeah.
I know we're not doing this yet, but when you said a picture of nuts and bolts, you mean like take a picture and upload that to MATLAB and then the computer can read it?
Yeah. It would be that, I mean, I give you some example pictures of like imagine there was a machine processing line, right? And on a conveyor belt, there's like nuts and bolts mixed, and there's a camera right above it, and it needs to figure out how many nuts or bolts there are as it's going by. So it takes a snapshot, it sends it to your MATLAB algorithm. The MATLAB algorithm comes back and says it's 4 nuts, 3 bolts. That's kind of the scenario. At one point, I actually wanted to create a conveyor belt and a jig with the camera and everything, and get it to actually feed into MATLAB. And I just like, that's for Keith. That's the kind of project for Keith. Hi, Keith. What was Keith's profound pedagogical?
Yeah.
What was it? That was hilarious. Any questions on this one? This one seems simple, pretty simple, right?
Yeah.
But I think in all of these problems, it's really the hard part is frankly the hard part is understanding the problem, figuring out the equation, and then figuring out what of it can you model, right? And that's kind of what Han does for you. But once you have this, that part's easy, right?
Would you be willing to work with us on the hard parts?
This part?
Like the blue on your part. Like,
I'm not sure I understand this.
Just like if we have trouble like trying to get our feet on the ground and you're running, like would you be willing to
Sure.
work with us?
Yeah.
Like, get on the project? Or?
Yeah. Absolutely. Yeah, for sure. Okay. I'm going to pull these equations. I have these equations in my notes, but I'm going to use these just in case. I didn't get a chance to double check that my notes were correct. Oh, that's not all there. It's okay. I'm not adhering to my border. Okay. So how many of you are taking regular physics, like the first physics mechanics, or have taken it? Okay, cool. Have you done the free fall problem?
Yes.
Okay, good. Okay. Have you done the free fall problem with air resistance?
No.
Sweet. Okay. So object falls, and what we're going to do is look at it in 3 different perspectives. Okay. The first one is no air resistance. The second one is air resistance proportional to the velocity. We'll just make sure that's correct. I think that's yeah, sorry, no, not exactly correct. Proportional to the power. Okay. And the third one is the air resistance proportional to the second power of velocity. Okay, and then in terms of what these approximate in the real world, the no air, that's basically the fake world, right? Or a world where there's no atmosphere. The one where you're linearly proportional to the power of the velocity, that's basically a scenario where you have laminar airflow. What that means is the airflow that's going around this object is very smooth. There's no eddies, there's no turbulence, etc. It's very, very smooth airflow. Like a bullet. Yeah. So if you imagine a bullet in free fall where the nose actually stays down, that would be laminar flow. Okay. So the second situation approximates laminar flow, and the third situation approximates turbulent flow. And the cool thing with the turbulent flow one is you can actually get to this really cool concept that everyone loves, but no one ever actually simulates, which is terminal velocity. So does anybody know what terminal velocity is?
Yeah, it's where you like balance out with the air resistance for weight.
Yeah.
And you can't fall any faster than that.
And exactly. Terminal velocity is basically the speed. You don't exceed that speed because of the force of the air resistance against the force of acceleration. Equals. All right, cool. All right, so I'm going to give you a slew of equations. These all come from Han, but it'll help us do the model. I'm going to put them on there so we can actually model it up here. And part of this is to just say, like, okay, let's talk about how we take equations that we might have and put them in a MATLAB program, right? Because it's not always easy. Yeah. It's also not very hard. It's just easy to make mistakes.
Quick question. Number 3, is that the acceleration essentially? What do you mean by power? Power of velocity.
Yeah, what do you mean by the power of velocity? What is the power? Like first one, the power of velocity? Right.
It is.
This was a good question.
Yeah, it's a good question.
Oh, we decoded it.
Yeah, let's just. I mean, so we're using like. Yeah, it's not intuitive to me at the moment. And again, this stuff is not fresh in my head, so. I know I can.
Well, we all
answer.
took it.
What's that?
We all did for it.
Okay, there you go. Yeah, you guys will know it better than I can.
Wow.
What's that?
The students have become the teacher.
That's awesome. I'm okay with that. All right, so situation number 1. Okay. Our acceleration, d squared dy dt squared, effectively g, right? Our velocity, dy dt, change in y over change in t, effectively gt. So the velocity's growth is going to be linear. And then the position. 1/2 gt squared. Okay. Second situation. we're starting with G and we're modifying it with this K dy dt. So that's strictly linear. And the K is the air drag parameter. Right, so velocity, dy dt. So here we have our G over K again. Oops. Okay, so sorry, this is where things get different. G over K times 1 minus e to the negative K. Yeah. And then Y. This is why I couldn't give that answer as easily as you guys wanted. Okay. Here, let's do those two first because I want to be able to see them while we do it in the program, and then we'll do the third case. Let's make sure that's right. Yeah, that looks okay. I realize it's hard for you guys to see it. Okay. So the first thing we want to do is set up some big vectors, right? Actually, the first thing we should do is define some variables. We got that. We got the air drag parameter, right? What other key input variable do we have here? We have gravity, right? Yeah. Oops. So make that G. 9.81. Okay, we're going to use 0.2, right? We can define our time step. Let's go from 0 to 5, and let's do a dt 0.01. Okay. And we'll go final t 5. Okay. So we have t equals, how do we make our t vector for all of our times?
1 to final t and dt times.
We'll start at 0. 0 dt 5. Okay. Good.
Should we do final t?
So again?
Should we do final t or no?
Oh yeah, sorry. Yeah, I should. Exactly. I should do that. Very good. And let's do velocity and y, right? So our equation for velocity was g times t, right? And our equation for the y distance is g times t squared. That's what I have up here.
You generally prefer multiplying by 0.5 as opposed to dividing by 2.
In sort of writing an equation out, I do prefer that. Yeah.
Do you
There's
recommend?
no rule that says you don't have to do it. Have to do it. I would recommend. I've always found it easier. But that doesn't necessarily mean that's easier for everybody, right? Like, I think you're free to make that call. Cool. So that's actually without friction. So let's be clear about that. Without friction. Oops. Okay, and then let's do y linear friction. So these equations look a little bit different, right? So I've got this second one down here. See that up there here? So help me convert this V equation. Can I do that?
No.
Time.
MATLAB does not like that at
Good
all.
start.
Yeah, that's it. How many of you got? How many of you have seen that already?
Oh, yeah.
Okay. How do I get Euler?
EXP.
EXP, parentheses. So what goes inside the parentheses is what's actually up there. So so the operation is the t times the k, and the k is scalar. So okay.
What about for the exponent function?
It handles. There's no matrix. There's no meaningful difference. Sorry. The exponentiation of a vector or a matrix is element by element by default. And yeah. Okay, how about the y linear friction?
G over K.
We got G over K again.
K squared.
Well, that's still coming, right?
G over K times T
Oh.
minus G over K squared.
Do I need the dot on the K squared?
K was the scalar, right?
K with scalar, right? Okay, so we're okay there.
Star
Star 1 minus
1 minus exponent negative K.
Now I'm confused. The book has. Okay, let's see. Let's see. The book has. Something that surprises me a little bit. Let's keep going.
This is what the book has, right?
Now the book has a dot in there.
Oh, as far as on the script.
Okay. All right, let's try this. And if we get some complaints. Oops.
Well, with that dot negative,
Yeah,
that might be like a typo.
yeah. Okay, cool. So now all I want to do is plot these guys. I want to plot both of them. So let's do that, right? So plot. How do I do this? What should I plot against? Should I plot V versus Y? Should I plot versus time? Yeah, so I have 4 things here I could plot against time, right? It probably doesn't make sense to plot the V and the Y on the same plot. Would you agree? Maybe? So let's just do velocity first, right? T, right? V without, right? And T, Okay, so before I do this, what do we think we might expect to see in these two lines? Like what difference do we expect to see between these two lines?
Without friction, your velocity is going to increase faster.
Okay,
With friction, your velocity, so the slope of the line will be steeper
yeah,
in the first plot.
yeah, absolutely. That's a good intuitive thought, right? What else? In terms of, do we expect a straight line or a curved line?
With friction, I don't believe it's straight.
Correct. But without friction, straight, right? Because that acceleration is acting effectively linearly. Okay. Good. Woohoo! Look at that. So this is the velocity rising, right? So I know we have an object dropping, but what we're seeing here is on the x-axis, time progressing, and as time progresses, the velocity is rising. Right? That makes sense. As we're following, the blue line represents the without friction straight line.
So you define positive as being downwards towards the earth?
That's what we have. In terms of the velocity,
Yes.
yeah. Well, we could reframe it. Yeah, super easy. I mean, that just requires us to change these equations a little bit, or just change the polarity. Gravity. Change gravity. Yeah, can you do that too? Yep, yep. You guys want to do that?
No, I think this is a good visualization of speed. Usually when a line is going downward, I consider that to be something that's
Slow it down. Okay. Okay. Should we plot the other one too? The y. What do we expect that to look like?
Isn't it the same line? Aren't we plotting
Just vertical.
a vertical line going downward?
It's over time.
Looks like a negative. Oh, it's over time. Oh yeah, so then we're decay. They would be sort of like the inverse, it's like opposite decay of the other line.
Because their progression in terms of their rate of change is going to slow.
Yes, yeah, exactly.
So, or sorry, no, the rate of change is increasing. So they're actually more curved. It's these two lines that are those. Let's actually, I don't like them on the same axis. Let's fix that. Yeah. How do you guys think we should fix it? Subplot or figures? Two figures.
Figures easier.
What's that?
Figures faster.
Two figures? So I haven't labeled these, but this is the one on the right is the velocity, right? And the one on the left is the displacement. Given a linear changing velocity, you're going to have a curved displacement changing from that, right? Okay, so let's do the third case. Shall we have the third case? And then we'll take a break. The equations get really cool on this one. So acceleration. G minus K dy dt squared. Here's that square on the velocity.
Well, so that's the proportionality. So dy over dt is velocity.
That's velocity.
Yeah,
Square
so
velocity.
K proportional.
But Okay, so what they meant by linear power of the velocity is basically a velocity of 1.
Yeah.
I think is that what? Yeah, yeah. Linear, the first power is linear. Fair enough. Velocity, 1/2 g over k, tangent h, g k squared t. Y equals 1/k on e. Yeah. So we do now v, what do we call it?
Instead of log this, we could do it written down.
Let's do it. Oops, this is where MATLAB opens. Hold on a second.
This doesn't have a G over K.
I'm looking at the wrong equations now.
For V,
Yeah,
this is, so square root.
yeah. Well,
You
in the narrative, it's not square.
yeah, exactly. Because you're doing V, right? So this says 1/2 G over K tangent. Maybe like, you know what? Oh no,
Yeah.
no, because there's the tangent right there.
He has some discussion in here. I didn't pay attention. Let's leave it. Let's do the equations that we have here. See what happens. Because I'm actually curious about why he did that.
Okay, he does another square root inside this too.
Yep. He's doing some terminal velocity substitution. Not completely sure. Okay, is that correct? Yeah. Okay. Let's do 1/k.
Don't you have to have the star in between the G, K, and P?
Yep. Yep. Good point. Okay, does it look right to you guys?
Maybe I haven't seen it.
Which one?
Log.
Oh,
Yeah, no. This is the log base 10 or base C.
I think it's E is the default. Yeah. And then log 10 is you have to be explicit about it.
Maybe subplots were better.
What's that?
Maybe subplots were better.
No.
Three.
You guys want to switch to subplots? Ah, you want to go around. Oops.
Missing an
Actually, sorry. What am I doing? I don't want another plot. I just want to add that here. Right? Ah. There you go. Cool. Yeah, I'm not sure why it does that square root substitution. I'll try to look at it later. I mean, we definitely get that terminal velocity data today, right? It probably would help to add legends to both of these, right? So we should do that. And we'll call it done.
and see.
Oops. What am I missing? Oh, thanks. Cool. Oops. Oh, I didn't share.
So did you define what H was?
H.
The tangent of H?
Oh, it's a different function. It's a specific function.
Oh.
So cos H is cosh.
Yeah.
I don't know.
The parameter to cosh H is what's inside the parentheses, and the cos it's a special function. It's a special treatment. Same with the tangent. Good question. Cool. Any questions or thoughts on this?
Can you upload this to Canvas when you have to?
It's actually exactly what's in the book.
Oh,
Or not exactly, but close to it. We skipped the square root first.
Chapter 12, correct?
Yeah, chapter 12 and this one. I'm not sure about the other one. The same? Okay. And actually, there's a circuits example that's pretty cool. There's another example that's pretty cool. Yeah. Cool. All right, let's take a break and then let's come back in over there. Yeah? And I'll stop the recording.
Can you go back to the gap control?
Yeah.
Yeah, just give me, I missed one part.
No worries. Let me. Okay, just be careful.